Even before a student has completed standard 10, grade 10, class 10, whatever you call that, in whichever curriculum that you're following, whether it's the national curriculum or the international curriculum, you would have heard the word quadratic equations. And the funny thing is that if you were to continue with mathematics in class 11, 12, or even beyond in college, you will find that quadratic equations is going to follow you even there, because there are certain trigonometric equations that can be solved using the methods of solving a quadratic equation. And likewise, there are certain exponential equations that can be solved using the methods of solving a quadratic equation. And therefore, it is very important to study quadratic equations. The first thing that I want us to all consider is, why is a quadratic equation called a quadratic equation? I'm emphasizing this word, quadratic, in that word quadratic equation, quad, okay? Because, a quadratic polynomial has the form ax squared plus bx plus a c. All right, that's the general form of a quadratic polynomial, where a is called the coefficient of x squared, b is the coefficient of x, and c is called the constant term. Okay, they can be real numbers, they can be rational numbers, depending upon the field that you're studying this quadratic polynomial under. Now, the degree of a quadratic polynomial is 2. Okay, the degree of any polynomial is the degree of the highest term in x that appears in that polynomial. So, cubic polynomial will have degree 3 because you have an x cubed term appearing there. A quartic polynomial has a degree 4 because the highest term in x has got the power x to the power 4 there. In the same way, the highest term in x is a square, the degree is 2. But unlike the other polynomials, like a polynomial of degree 3 is called cubic, okay? 3 cubic, that makes sense. Degree 4 quartic, that makes sense. But degree 2 and quad, quad suggests 4. Think about it. I'm not going to give that answer in this particular video. In the videos that will follow, we will explore that. But I want you to think about it. And if you find out, please mention that in the comment, okay? But it's a question worth thinking. Why is the name quadratic or quad involved in that word quadratic equation when the degree is actually 2? Unlike the other polynomials, like I said, right? Cubic, degree 3, that makes sense. 3 cube makes sense. But when the degree is 2, why is it still called quadratic, where quad actually is associated with 4? The second thing that I want to highlight is the shape of the quadratic curve. That's called a parabola. Sometimes both these words, the quadratic and the parabola, are used interchangeably because, it's interesting that a parabola is a geometry, something that you study in geometry, and a quadratic equation, the methods of solving the quadratic equation, factoring, completing the square, quadratic formula, we sometimes study in algebra. But it's good that a quadratic and a parabola are used interchangeably, because it's only when we are able to see the geometry and the algebra together can we actually appreciate the beauty of these methods, what the solutions mean. So I'm also going to use these words interchangeably, quadratics and parabola. The shape is also quite interesting, okay, because as you can see, this is a fast shutter speed picture image of a tennis ball that's looped up, okay, and you can see that it takes that parabolic path, okay. So also this water fountain, as you can see, right, that's a parabolic path. Projectile motion is sometimes associated with this parabolic path. But the definition of a quadratic that really brings the algebra and the geometry together is this idea of second differences. Let me explain, all right? So if we make a table of values, I'm just going to call this x, okay? You could call it list 1. And here we're just going to enter some, the first 5 natural numbers, all right? The key thing to observe here is the difference between 2 consecutive natural numbers is the same. It's constant. We're going to call it the first difference, okay? The first difference for this column is basically something like this, right? So we have 2 minus 1 is equal to 3 minus 2 is equal to 4 minus 3 is equal to 5 minus 4. Okay, this could be any number, all right? We're just choosing the simple ones to make this point clear. And this is equal to 1, which is a constant. So the basic idea is that the first difference, that means the first set of differences of this list called X, is a constant. Now, if you have a second list, let me call that list 1, where it is not the first difference that is constant, but the second difference. Okay, let me just make up some numbers here. Suppose this was 1 and this is 4 and this is 9, 16 and this is 25. And if we take a look at their differences, okay, so I'm just going to call this first difference. And remember, this column that I'm writing first difference is talking about the difference, the first difference of the numbers on list 1, all right? So we are looking at the differences here. So this is going to be 4 minus 1. This is going to be 9 minus 4. This is going to be 16 minus 9. And this is going to be 25 minus 16, okay? As such, as you can see, that the first differences of the list 1, elements in list 1 are not equal like we saw for the list X, okay? They are all equal in the first go itself. The first difference itself was equal. Let's look at the first difference on list 1, okay? Here's going to be 3. Here it's going to be 5. This is going to be 7. And this is going to be 9. All right. Now, if we were to consider the second difference, that means it's going to be the difference of the difference, okay? The difference of the first differences, okay? So that means we're looking at 5 minus 3, okay? That's coming from the first difference, okay? And remember, these are all talking about the first and the second differences are talking about the elements from list 1, okay? Let's not forget that. 5 minus 3, 7 minus 5, and 9 minus 7. And when we work that out, we get that they are all the same and they are constant. It's not that they're equal to 2, but they're constant. The second differences are equal. And if we were to plot these sets of points along the coordinate system, that means along the x-axis, we've got this list of numbers whose first differences are constant. And along the y-axis, we've got a list 1. You know, I deliberately did not call it y initially, but if you've got a set of numbers along the y-axis whose second differences are a constant, then we would get a parabola. Let's find out. So this is our graphing calculator. We're just going to go to list and spreadsheet page. And here we are just going to call it X. And here I'm going to call it this list 1. All right. Shall we do that? List 1. Okay. And we just had first 5. So what we're going to do is that 1, 2, 3, 4, and 5. We're just going to call it 5. All right. And here I made up these numbers. So 4 and 9 and 16 and 25 and 25. And just to demonstrate the differences, what we're going to do is that just make sure that we will, I'm going to call one more, I'm just going to call this diff 1 for difference 1, okay? And the next column, I'm going to call it diff 2 for difference 2. And remember, these difference 1 and difference 2 are for the numbers on list 1, which is B, coming from column B. Here we can actually enter a formula, right? So this is something fun. What I'm going to do is that I'm just going to go to menu, data, and I'm just going to say list operations. I'm going to say difference list, okay? So, and the difference list comes from B, right? So I'm just going to say B, and there we go. We've got the difference. So it's 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7, and 25 minus 16 is 9. Difference 2, all right? So here we're going to have the difference from column C. So again, we're going to do the same thing. Let's go to menu, data, and we're going to go to list operations, and we're going to say difference list, this time coming from the column C. And we already saw this thing, okay, that the second difference for this list was the same. What we want to do to explore this is we're going to go and do a scatter plot, okay? Scatter plot means the points as it is. It's not the graph. That means it's connecting all, but we're just going to put X values, this list that comes from A, where it's a constant difference, okay? The first difference is constant, but list 1 will go along a y-axis where we have seen already here and on the calculator that the second difference is constant, okay? So what we're going to do is that I'm going to go and plot, enter graph page, okay? On a graph page, we don't want this one. This time we're going to go and say we want a scatter plot, all right? So let's just evoke that. X's are coming from this list called X, okay? That was not a very original name. And the Y's are going to come from the column which was called list 1. And when I say hit enter, okay, I can't see all the points, of course, because, you know, the zoom settings have to be adjusted. So we're going to go and say Windows Zoom Data. Okay, that's a nice option. And we can see something, okay? We can't see all of it. And perhaps it looks like a parabola. And by the way, this is different from the parabola that we saw earlier on. Okay, so that was interesting because here we've got what's called an inverted parabola. And even here, the ball looks like an inverted parabola. But you can have a parabola that's U-shaped or inverted U, depending upon the sign of this coefficient of x square. Okay, when A is positive, you get a U-shaped parabola, and when A is negative, you'll get an inverted U like this water fountain and the ball. All right. So when we get back to our calculator, we can see that this is a U-shaped parabola, but it's still too wide and we can't see what's going on the left-hand side. So let's add some more points, maybe some negative values. And so what we're going to do is that just to make it a little bit more faster and fun, we're going to make use of the function secant function, and I'm just going to enter the formula as I just need n in terms of n, starting from, let's say, -50 all the way up till 50, and I want them, that should be comma, sorry, all the way till 50. I want them increasing by 1, and there we go. It'll say, do you wish to proceed? The data is going to overwrite, and that's okay. And here what we want is we want the squares of the terms there. So I'll just say the squares from list A. All right, here we go. And that's going to overwrite the data. That's all right. As long as the second difference of that list is the same. Okay, we can see that, all right? This is in some other form. That's all right. If you want, you can change the setting again. So I'll just go to the settings and document settings. I'm just going to make this exact and come back to the current document. And there you can see that, all right? Now, the main thing is that here we've got a large set of data all the way from negative. I'll just scroll down quickly to positive. So can you see that? All the way up to positive 50, it should go. List 1 is actually the squares of those terms. And the main thing to notice is that the difference, the second difference of list 1 is constant. Whereas the first difference of list, the column A, which was X, is a constant. And now when we look at our scatter plot, remember it's a scatter plot, it's not a graph, okay? The points are plotted as they are. So that means 41 is the X coordinate, whose Y coordinate is going to be 1681. Let's see what the scatter plot looks like. Okay, we can't see all of it because we need to go and zoom again. So Windows zoom, zoom data, and voila. Just like that, we have a U-shaped parabola. And this is why this particular idea of the quadratic is so helpful to see the connection between the algebra and the geometry. The idea being that the terms on the y-axis, their second differences are a constant, whereas the terms on the x-axis, their first differences are a constant. We are going to continue our discussion on quadratic equations in the next video. Don't miss that.